Here we're going to talk about the exponential parent function. In general, it can look like that: y equals b to the x, and b can have several values. Could be equal to 2, 3, 4, could be equal to 1/2, 1/3, 1/4, could be any fraction, 2/5, or could be anything. Here what we're going to study is when the base is equal to 2, when the base is equal to 3, when the base is equal to 1/2, and when the base is equal to 1 cube. And you see that the calculation is already done. I'm going to narrate what is happening and how we get it. Alright, so here's the exponential parent function that generates all exponentials. And the simplest possible exponential is when the base is equal to 2. That generates all the exponentials with base 2. How does it look like? Well, it's going to look like that, but with b equal to 2. So it's going to look y equals 2 to the x. That generates exponential that could be look like that: y equals 5 times 2 to the x plus 3, or y equals 3 times or negative 3 times 2 to the x minus 1 plus 6. Things like that. As long as the base of the exponential function is equal to 2, it is generated by this parent function, and I get the graph of the transform function of this complicated function by transforming, stretching, compressing, shifting the graph of these simple functions. Okay, how do I start? First I need to do the chart. 2 columns. One is the x column, this is the y column, and I remind myself that the y is equal to 2 to the x. That's the rule. When it comes to exponential, I assume we have done the analysis explaining why we only need 3 values at the minimum. We can have more, but we shouldn't have less than 3 values. We have done all the explanation, the investigation, the discovery, and now we're just applying. There's going to be 3 values: 0, 1, negative 1. Those are supposed to be plugged in for the exponent. Then the next step is plug it in, so I get 2 to the 0, 2 to the first, 2 to the negative first. Now let's see what each one of those is. 2 to the 0 power is 1. So that gives me the point 0, 1. Let's write it here. Next is 2 to the first. 2 to the first is telling me multiply the base, which is 2, by itself 1 time, so that's just 2. So I get the 1, 2 point. And last I have the negative 1. I plug it into the exponent. Negative 1 is telling me flip the base, and then the negative goes away and becomes positive 1. But 2 to the positive 1 is just 2. So what I get is 1/2, meaning when and I have x equals to negative 1, y equals 1/2, so I get this point. Now let's plot those points. That's the 0, 1, 1, 2, and negative 1, 2. And I see that the curve, it's a curve, it's not a line. It looks like that. Now if I keep plugging in bigger negative numbers, it's going to get shorter and shorter and shorter, and it's going to go forever to the left, trying to touch the ground, and it's not going to touch the ground. Therefore we say that the ground is a horizontal asymptote, means it can't be touched, it can't be crossed, but it always try to approach it closer and closer and closer. So if you keep going like this and you go 100,000 miles to the left, it's still not gonna be able to touch it, but it's gonna be so close that we're not even gonna be able to distinguish. Still, if we zoom in, There's going to be a gap between the curve and the ground. Now, what's the equation of the horizontal asymptote? The equation of the horizontal asymptote is y equals 0. Essentially, the horizontal asymptote is the ground. And all the points of the ground, for example, this one, has coordinates 0. That's negative 3, 0. This is negative 2, 0. This is negative 1, 0. All the points on the ground have coordinates, y coordinate equals to 0, 0, 0, 0. So the equation that expresses the ground, which is the x-axis, essentially is this one. We're almost done. What's the y-intercept? Well, it's obvious that the y-intercept is 1. What about the x-intercept? Remember, it doesn't touch the ground, never, so there is no x-intercept. This symbol here means there is not. Okay, that's a mathematical symbol. If there was, then we would put that there is. How about the domain? Well, the domain I'll find if I project on the x-axis. So let's start projecting. From here, I go like this. To the left forever. I go like that. To the right forever. And I cover the entire x-axis. A way to write this is like that, meaning all the inputs are between negative infinity and infinity. That's what the domain means. All the inputs, the set of all inputs, and the set of all inputs are the set of all x coordinates, which can be any number on the x-axis. So we put the x between the negative infinity and the infinity. We don't put equal. Remember, we can't reach infinity. And another way to write that, because between negative infinity and infinity are all possible real numbers, is like that. The domain is equal to R. When you write the R with a double line, means real numbers, all real numbers. What about the range? Here we're going to write the range. To find the range, we have to project, but not on the x-axis, on the y-axis, because the range is the sum of our outputs, which are the y-coordinates, and those are on the y-axis. So let's start projecting. I project towards the y-axis, and I keep going forever, and then I cross this point, and then I project again towards the y-axis. Eventually I will cover the upper half of the y-axis, but I'm not gonna be able to project anything at 0, because to project I would have to touch the x-axis and then project it. So the 0 is not included in the range. Okay, how do I write this? Same format, only for y, and it needs to be between 0 and infinity. The lowest point is 0, but I can't touch it. There is a hole there, and it keeps going on forever all the way to infinity. That is the exponential parent function when the base is 2. I do something similar for the exponential parent function that corresponds to base 3. It's going to be equal to 3 to the x. Now I can go a little faster. The inputs are 0, 1, negative 1, as always for all exponential parent functions. The first step is easy. I just rewrite the rule, but for x I put 0, 1, negative 1, so that's easy. Now let's evaluate. 3 to the 0 is always 1. 3 to the first is 3. 3 to the negative 1 is 1 over 3 to the first, which is 1 over 3. So those give me those points, 0, 1, 1, 3, and negative 1, 1 over 3. If I plot them, I'll get those points. I connect them, I get an exponential that it grows faster than the previous exponential, which all exponentials grow fast and then drop down to the asymptote. This is also grow fast and then drops down to the asymptote, but it's faster than the previous one because the base is bigger. It will have an asymptote which is going to be the ground, meaning the x-axis. The equation is still going to be y equals 0. What about the rest? Still the y-intercept is going to be 1, no x-intercept. The domain is all real numbers, or any, includes all inputs between negative infinity and infinity. And the range is still going to be the upper half of the y-axis, except for 0. It has to be greater than 0, not greater than or equal to 0. And that is the parent function, the exponential parent function y equals 3 to the x, that has 3 as the base. Let's go to the next one. The next one, the base is a fraction, is 1/2. Still gonna do the same thing. 0, 1, negative 1 for the inputs. I see the rule 1/2 to the x, so the first step I put for x 0, 1 and negative 1. The next step I have to evaluate. Anything to the 0 power is 1. Anything to the first power remains unchanged, and anything to the negative to a negative power flips and the power becomes positive. So here 1/2 becomes 2 over 1 and the power becomes positive. Now of course 2 over 1 is just 2 over 1 to the first power is just 2 over 1, and then because the first power means just take whatever you got and whatever you got as the base and don't change it, and then 2 over 1 is just 2. So what do I get? I get those 3 points. I plot them, and once I connect them I see that it grows, but it grows on the negative, on the second quadrant, and it drops down towards the ground, trying to touch the ground, which becomes a horizontal asymptote on the opposite side. So if you compare this exponential with the 1/2 as the base with the previous 2 cases, we see that the previous 2 cases grow on the right, drop down on the left. This one grows on the left and drops on the right. How about y-intercept? Well, I see the y-intercept is still 1, no x-intercept, and the domain is all real numbers, the same as the first one, or that can be written in using inequalities or the symbol, and the range is still going to be the upper half y-axis without 0, so y needs to be greater than 0. Okay, now let's go to the last one. The last one has base equals to 3, so the parent function is y equals 1/3 to the x. How do I do its graph? I start with a chart, the usual 0, 1, negative 1. Plug in into the first step, so you have 0, 1 or negative 1. Anything to the 0 power is 1. Anything to the first power remains unchanged, so 1/3 to the first is just 1/3. Anything to a negative power flips, so 1 over 3rd becomes 3 over 1 and the power becomes positive. And what's anything to the first power remains unchanged, so 3 over 1 to the first power is basically 3 over 1. Now 3 over 1 is of course 3, and that gives me those 3 points: 0, 1, 1/3, 0, 1, 1, 1/3, negative 1, 3. I plot them and I get those 2. I see that it resembles the previous case that grew on the left. It also grows on the left and it drops down on the right. And now that is going to grow faster than the 1/2 case, okay, and it's gonna going to also drop faster than the previous case. Let's do some attributes. Y-intercept is 1, no x-intercept because there is an asymptote, the usual asymptote on the ground, horizontal asymptote. Domain is all real numbers that can be written two ways, with inequalities or with a symbol, and range is the upper half of the y-axis except for 0, so don't put equal here. And that's it. Those are the most usual cases that you will see in algebra 1. 2 to the x, 3 to the x, 1/2 to the x, and 1/3 to the x. Notice